Classes in Statistical Mechanics. Lectures by Professor George Phillies, based on his book, Elementary Lectures in Statistical Mechanics, Springer Verlag, 2000. And today, this lecture is Lecture 25. Today we're going to start off by completing our discussion of the Langevin development that turns into something completely systematic, namely the Mori-Zwanzig equation. Last time we'd reached page 356, in particular equation 26.42. And 26.42 is an equation for the time evolution of A prime. It has a formal solution for the homogeneous part, which is an exponential of the differential operators on the left side of 26.42. And that is the first term on the right of equation 26.43. That is, it's the exponential of t I minus pl of A prime. And that's the formal time evolution solution of A prime of 0. Now, that's a time evolution operator, but it's a little peculiar in one respect. Namely, the time evolution is not given by the Liouville operator L, but by its projected part I minus PL. And the projected part of the time evolution operator may be somewhat different than the time evolution operator itself. The second term in 26.43 arises because 26.42 has a source term, everything on its right side, and everything on the right side of 26.42 is the source, and then the source contributes at various times from 0 to t times s, and then the object evolves from s to time t, and there's a time evolution operator for that. And that is given as 26.43. However, if you look back at equation 26.38, 26.38 makes fairly clear if you go to time 0, A prime is I minus P of A of 0, and guess what? We're projecting with respect to A of 0, so I minus the projected part of A is A minus A is 0, and therefore A of 0 is 0, and A prime of T is then given only by the second term in 26.43. Okay, so in understanding 26.43, we first see that the first term in on the right is 0. There's nothing there. The second term we can reinterpret. That is, we can say that the exponential of all that stuff times k of 0 is the part of is the source term, and psi of s serves to propagate that forward from time s to time t. Okay? Note, now, as I said, there's a projected time evolution operator there, and the projected time evolution operator says that we're seeing a time evolution which is not the same as the full time evolution operator. And that is somewhat significant. Okay, we're now going to introduce a new mechanical variable, f. And f at time 0 is k at time 0. And f at time t minus s is the propagation forward in time from time 0, except the propagation is described by the projected time evolution operator I minus p of l. The above pair of equations, 2644 and 2645, define the variable f. Now, what is the variable f? Well, the variable f picks up, as k goes forward, the time evolution operators sort out from k of 0 the parts of k, of the evolved k, that are not correlated with a. That's what the I minus p does in the Liouville operator. And because you are sorting out the projected parts, you're only, at all future times, f is not going to be correlated with a of 0. Yes? Does this sound familiar? Yes, it sounds like the random force, which was never correlated with the initial velocity. And little f turns out to be very much like the random force. However, there have been no ad hoc assumptions put in as to what f is. Instead, all we've said is we have a k of 0, which we defined on page 356, and it was k of 0 is I minus p a of 0, which is 0, or would be if we completely evaluated it. No, I minus p a dot is not 0. I take that back. I minus p of a dot is the part of dA dt that is not correlated with a of 0. And so it's the part of the change in a that's not correlated with a of 0. And it's time we pull out of k of t, or k of 0, the parts of it that are not correlated with a of time 0. We will now show below that the f, as defined here, has the properties expected of the Langevin random force. The form of the proof is to find an equation for dA dt, and we'll transform it into something that looks like the Langevin equation, except we'll do the transformation purely mathematically. There will be no hand-waving whatsoever. There will be a memory kernel phi. The memory kernel phi is determined by a time correlation function of f, so f and phi are related by a fluctuation dissipation theorem. This time, however, the random force little f is purely formally and rigorously defined. You may or may not like the definition. You could define some other random force, but it's a well-defined mathematical quantity. And the source term of this new equation is little f itself, so little f behaves exactly like the Langevin random force, except we actually derived it. Okay, so what do? We take equation 26.45 and we stick it into equation 26.43. And if we stick it into 26.43, we notice that, and then stick that into 26.40. What do we have? 26.40 says that a of time t is psi of t a of 0. That is, a of time t has a part that's correlated with a of time 0, and it has another part, a prime of t. And we take a prime of t, which is 26.43. On the right of that, the first term is gone, and the second term is psi of s, f of t minus s. That is, that exponential times k in 2643 is the definition of f at the right time. And therefore, we have an equation for the time evolution of time a in terms of psi of t and the integral psi of s f of t minus s. Okay? Now we claim the system has time reversal invariance. Red alert. I have just said the weak interaction is not usable. Why? The weak interaction does not have time reversal invariance. The weak interaction can tell which way time evolves. There are some other issues with the weak interaction. Also does not have CP invariance. And this is sort of required, so the weak interaction has CPT invariance, which most people think is a requirement that you can't avoid. Until the laws of nature are changed by the high energy people again. In any event, from time reversal invariance, I will write this as a of minus t, so I have a psi of minus t, a of 0, and an integral from 0 to minus t of the source term. Now let's look at 26.47, or 26.46. There's an integral ds, and the integral ds is a convolution integral. What is a convolution integral? We have an a of s, b of t minus s, and the integral ds goes 0 to t. And therefore, psi of s takes all values between 0, s takes all values between 0 and t, and t minus s takes all values between t and 0. Yes? Well, that means I can interchange the two variables as I do in 26.48, and I replace s with t minus s, and I replace f of t minus s with f of s. And I can do that because it's a convolution. And in the integral, all products psi f are represented equally by 4648. The first time you see this stunt done with a convolution, it looks really weird. But if you check a few intermediate points numerically, you'll discover it works fine. It just is something you may never have seen before. Now I will reach in and I will take the time derivative of equation 26.48 with respect to t. Well, that's perfectly legal. T is a variable. So on the left side I have dA dt. On the right side, well, c is a function of t, so I get dc dt. And you see a d psi dt from the first term, and you see a d psi dt from the convolution. And also, because I am taking d dt, I get the time derivative of the kernel evaluated at each of the two limits times the derivative of the limit with respect to t. Well, d0 dt is 0. That one drops out. dt dt is 1, and I get the kernel at the limit. So I have psi of t minus t, or psi of 0, which is 1, times f of t. There is f of t. And I have now reached equation 26.49. And if you look at 26.49, that's starting to look like the Langevin equation, isn't it? I have a plus f of t out in the back end. I have two intervening terms, and in order to evaluate those terms, I need the time derivative of psi. Let's go back 2 pages, and I remind you what psi is. It's 26.36. It's correlation function a of 0, a of t, and it's normalized by a of 0 square. So we're taking the time derivative of a of 0, a of t. Okay, well, let's actually take 2636 and take the time derivative of each side. And on one side we get the d psi dt we want, and on the other side the d dt goes inside the ensemble average, because the one place it can attack is a of t, and now we have an a dot of t, the time derivative. That's 2650. Push ahead. Okay, now we're going to define a projection pt. New projection operator. The projection operator pt does the projection not with respect to a at time 0, but with respect to a at time t. Of course, you want to calculate this, you would have to reach in and calculate a of time t in terms of a of time 0, or you would have to cheat and notice, if you're lucky, that we're looking at an equilibrium system, and on occasion you can use time translation invariance. So there's the projection operator, and I am now going to write the identity operator in terms of the projection operator, namely the line after 2651, the identity operator is I minus p sub t plus p sub t. This is a very complicated way of writing the number 1. And we will insert that into 2650. And if I insert that into 2650, I get the d psi dt. Okay, the I minus p part of the identity operator is now inside the first correlation function on the right of 26.52. So I have an a of 0, I minus pt, a dot. Yes? The second time I have p sub t, so I will take the projection with respect to p sub t of 2650. And I have taken that, and when I take that, I get the second term in 26.52. And that's one of these you actually have to put things in and turn the crank. And what has happened is there's a correlation function a of 0, a dot of t, and the p sub t replaces the a dot with a somewhat complicated object which you get to write out. And so you have a star of t, a dot of t over a t squared, a 0 of t, a t of square over a 0 square. And that is simply a matter of you stick the p sub t into the correlation function and turn the crank, and there's nothing much there. Okay, so what have I done? I have decomposed d psi dt into two parts. And one of the two parts is a part that is correlated with a at time 0. That's the first part. That is I minus p a dot, first term in 2652, the I minus p a dot is multiplied by a of 0, and a correlation function, an ensemble average is taken. So that term only includes the part of I minus p a dot that is correlated with a of 0. And then we have the other part. Yes? Other part has some weird pieces. Okay, well, one of the pieces is a of 0, a of t over a 0 square, and that is simply psi of t. That's simply the definition of psi of t. Then there's the part a of 0, a of t, a dot of t. But I can use time translation invariance. Everything in the first term, in the first fraction of the second term of 2652, only depends on the time t. Yes? Well, therefore, whatever that average is, it's the same as the average would be at time 0. So I can replace in the denominator a of t average square, which with a of 0 average square, that's time translation invariance. I can replace a of t, a dot of t, with a of 0, a dot of 0. Yes. And what did we just do? How did we get time translation invariance to work? Well, a of 0, a dot of 0 is something else we know. It's I omega. If you don't believe me, go back on page 2637, page 355. I omega is a of 0, a dot of 0. That's the first part of the last term of 2652, and that becomes the I omega of 2653. Now I did one more thing in 2652. 2652 is a of 0 times k of t. Well, I will step that average backwards in time, so it becomes a of minus t k of 0. Yes, I just did time translation. I can do that because I am in an equilibrium system. But what is A star of minus t? Well, A star of minus t is something we know, namely it is given by, where'd it go? Equation 2647 complex conjugated. Yes, 2647 gives me A of minus t. I'll now take its complex conjugate, and that gives me A star of minus t equals, we're 2 lines above equation 2654, this piece. Having written out this piece, I now combine everything and I get equation, oh, there's a typo. That should read equation 2653 then becomes equation 2654. See it? It's equation 26.54. Yes?
Mm-hmm.
Well, psi of minus t, I can do it by direct substitution, the line after 2654. It's A star of 0, A minus t. So I'll now do time translation, A star of t, A of 0. That's time translation. So is equal to psi star of t. That's just because the last piece, the next to the last equality, is psi of t complex conjugate, and therefore I can replace psi star with psi. Furthermore, k of 0, psi star of minus t, A of 0, I can rewrite. I have rewritten, and I can pull the psi of star of t because it's just a number outside. And if we look 3 lines below 2654, there is that object k of 0, psi star of minus t, A of 0 star. And I can pull the psi of t outside, yes. And having pulled it outside, I have an A star of 0, and I can write k of 0 in the indicated form. And that vanishes. Why does that vanish? Because A at time 0 and I minus PA of anything vanish, because I minus PA of anything is uncorrelated with A. And therefore that term vanishes, and it vanishes for arbitrary B. Oh, I put in a B not equal to A and the 4th line down. That should just be B. The form vanishes for anything, yeah, arbitrary B. Having done that, we can now rewrite this thing a bit further. We can. Oh yes. We can rewrite things, and we have d psi dt, the left side is the same, is equal to I omega dot psi, that's the same. And then there's an integral 0 to t f. And if you check the math, there is a little piece missing, but you end up with, there's a little piece, must be a little piece missing in 26F54, because if you check all the math, you get a psi of minus s, f star of minus t minus s, f of 0. And I would have to we would have to do the math out on paper. I will tell you to do, that's your last homework assignment. Get from 2652 to 2655 and find the f of 0 that someplace has gone wrong. Oh, I know where it went. In fact, I tell you. In the integral, I have replaced k of 0 with f of 0. That is, if you go back there I'll tell you what the homework answer is. In 2654, the big fraction on the right, first right-hand term is k of 0 times all this stuff. Well, k of 0 is a number. You can pull it inside the integral. And k of 0 is equal to f of 0. So that's where the f of 0 came from. Okay? Now we're going to do a change of variables. We will replace the variable s with the variable minus s, which changes the limits from 0 to minus t to 0 to t. It changes f star of minus t minus s to f star of minus t plus s. Yes. Then we will do time translation and variance to replace f star of minus t plus s, f of 0, to f of 0, f of t minus s. You see, we did a time translation and variance forwards by plus t minus s to get that. And after we've done all this, we notice, gee, we've got a convolution again, and I'm going to do that convolution trick one more time. And when I have done the convolution trick one more time to replace psi of minus s, which is now psi of s because we did time reflection, I replace psi of s with psi of t minus s, and f of t minus s with f of s, and I get 2656. So far, so good? Now we say the last fraction in 2656 I am going to define as phi of s. So phi of s is f of 0, f of s over a of 0, a of s with some complex conjugates woven in. And that gives us equation 2658 for d psi dt. Namely, d psi dt is 2658. Check. Okay, now we know what d psi dt is, and we can now plug d psi dt in 2649. 2649. We sort of got lost, but 2649 had some d psi dt's in it. We've now evaluated d psi dt. This was this little loop off to the side to evaluate d psi dt, and we've now come back in a circle to 2649, and we stick in for d psi dt, and we get equation 2659. Yes? Okay. Now we do a final rearrangement, and we note that the first term on the two lines of equation 2659 are I omega a of t. Furthermore, the terms in phi of s and phi of u, if you look carefully at 2659, jointly yield an a at time t minus s, and therefore we can write 26.60. And essentially what we said is we can do that last rearrangement because it's something from previous equations, and we just keep doing substitutions that are identities, and we reach equation 26.60, which is the Mori-Zwanzig identity. The one thing that is not what have we done to do this? We have used projection operators. We have used time translation and variance, which is saying this is an equilibrium system. We have used, that's about it. And we got to the Mori-Zwanzig identity. In the equation 26.60, the kernel is a memory function. It shows how the relaxation rate of a, dA dt, is affected by A at earlier times t minus s. Or if phi of s is very short-lived, could be the case, if phi of s is close to a delta function, we saw that it's the Langevin equation. Phi of s becomes delta of s. The integral from 0 to t ds is only non-zero right at time 0, and the second term of 2660 becomes constant times a of t. And in that case, we have dA dt is I omega a of t plus constant times a of t plus little f of t. Yes? Does this look like the Langevin equation? Well, it does, except for this I omega. However, in most equilibrium systems, capital omega is always is 0. It's not 0 because Mori stuck something in to handle, for example, systems in magnetic fields, Bloch states in magnetic fields, which you get in nuclear magnetic resonance, in which there is something oscillating in time. Well, but in general, the I omega term vanishes, and the thing that corresponds to Stokes' law of friction is the phi of s, delta of s. Okay? Now, there are some generalizations of this that I did not put into the book. The most important generalization is to say we are talking at the moment about a variable a. However, the variable a could be a vector, that is, a list of scalar variables. It doesn't have to be a 3-vector, just an ordered list of quantities is a vector. If we go through this derivation again and repeat it, treating a as a vector, we would get a relaxation equation involving a coupled set of variables. When would you be interested in a coupled set of variables? Well, suppose we have a simple liquid. The simple liquid is characterized by the following variables, simplest case. There's a physical density, a number density. There's an energy density, or some people would erroneously say temperature. These people are heretics and should be burned at the stake. Or you would say there's a momentum density. Okay, so that's, since there's px, py, pz, that's 5 coupled variables. And what do the 5 coupled variables do? Well, they give us, if we look at the density fluctuations, which we can see with light scattering, we actually can go in, do the calculation. There is a calculation that was done by Mountain and Deutsch. There is a calculation that was done by Phillies and Kivelson for the case that there was also a chemical reaction going on. In either case, there were these 5 variables, or maybe 6, and you can calculate what the spectrum of density fluctuations look like. And there is a fluctuation which sits around 0 frequency and corresponds to local energy fluctuation, and the heat flows out and the density relaxes, and that is a central Rayleigh line. And then there are thermally excited sound waves in the system. Those are Brillouin lines. And then the Rayleigh and Brillouin lines are coupled to each other, and there is what is called the mountain line, which is buried in this, and you get the spectrum of light scattered from a fluid at equilibrium. And to do that, you need a bunch of variables. And you can add extra variables, hydrodynamic variables, if you want. If you talk about liquid crystals, there are bunches of additional variables. They're called order parameters. and the coupling to the order parameters and maybe their gradients and such not tells you things about the liquid crystal. Okay, however, if you did the vector form of this, all of these quantities like a of 0 square and omega and the memory kernel are no longer numbers, they're now matrices. If you have n variables, they become n by n matrices, and you have to calculate them. Okay, let us now do some, so that is the Mori-Zwanzig calculation. And I am telling you there is a more complicated form if you want to handle multiple variables. It may occur to you that saying I have multiple time-evolving variables in a matrix sounds remarkably like quantum mechanics, and you can do a quantum Mori-Zwanzig calculation. In fact, my last master's student, Rachel Nasto, actually did this, and it works. Now we will do some asides. So what math assumptions actually went into Mori-Zwanzig? Okay, we have a set of basic variables gamma. In our case, the variables gamma were conjugate pairs of phase space variables, but we never really used that fact. We have an interesting object that can be identified one-to-one with the values of gamma, a point in phase space. The object evolves in time by moving through phase space. We did not, however, ever use the fact that the Liouville equation is simply a different way of writing Hamilton's equations of motion. We just said there is a time evolution operator, I don't care what it is. And the time evolution operator, L, uses its time-dependent inputs only the current location in phase space, nothing else. We have an averaging process, and yes, I always said ensemble average, but we never ever used the fact that the average is the ensemble average. Furthermore, the averaging process and the time evolution operator are consistent with static and dynamic time translation invariance. So if we calculate the mean square value of a variable at time 0 or at time t, we get the same answer. And if we calculate a of 0, b of t, or a of minus t, b of 0, two variables separated in time by t, we get the same answer if we translate things. Now, that is invoking the prior chapter on stability of the canonical ensemble. The statement that the canonical ensemble is stable, is time stable, says that the time correlation functions have time translation invariance. Those math assumptions are very general. This is a very general way of doing an equation that describes the time evolution of a functional on some space. The time evolution operator has to have those stability requirements, but once it does, this is very general. Now we come to the standard application. We say we can look at all of the mechanical variables there are, and we shall divide the set of mechanical variables into two parts, fast and slow. Yes? The slow variables are the variables whose projected decays are slow. That is, they have variables that are long-lived memory functions. The fast variables are the variables whose projected decays, projected time evolution decays are fast. That is, they have short-lived memory functions. So we can do this separation. If this is the case, the phi, the memory function, is a delta function, or if you have a bunch of slow variables so that A is now a vector, and you've got to be careful all the way through with matrices being left multiplied or right multiplied. That you really have to be careful with. That's why I didn't do it in the text. the Mori-Zwanzig identity becomes a set of cross-coupled differential equations. The memory kernels are all delta functions and integrate out, and you are now left with a set of coupled differential equations. And they're coupled linear differential equations, which you can solve. If the set of slow variables is incomplete, then some of those memory functions are long-lived, and instead of what you would hope for, you instead get integrals over long-lived memory functions. Now, the calculational approach, standard approach, you aren't forced to do this, say we will choose for A all of the slow variables, which means we have to figure out what they are. And having done that, the memory kernels are nearly all delta functions, and we get coupled linear differential equations with constant coefficients. You aren't forced to do this. There's no guarantee that the variables can be separated into fast and slow. That is, there might be slow, slightly less slow than that, and no matter where you truncate, you need some memory functions. Okay, the Langevin equation is an example of this. And now we come to what you actually do. Well, you can choose the slow variables in several different ways. I mentioned the Mountain, Deutsch, and Phillies Kivelson calculations. They're calculations of the same thing. Mountain and Deutsch chose their variables, so whenever they evaluated A of 0 squared in the denominator, which is this big matrix, they chose their variable so A of 0 squared was a diagonal matrix. And that's very nice because that meant the A of 0 squared was well behaved. It also meant they had this particular set of variables, and the coupling of those variables to the index of refraction and thus to the light scattering spectrum got a bit messy. We did the other approach. We said, we will choose our variables so they couple nicely to the index of refraction, so that d epsilon, d1 variable, is important. D epsilon, the other variables, all vanish. And therefore, or at least one of them vanishes, and therefore our coupling to light scattering is fine at the price that the matrix in the denominator is full of terms. And then you have to evaluate the full of terms. And the full of terms means you have to turn all of those terms into thermodynamic derivatives on reasonable variables. And so Kivelson and I had the assistance of Bob Scott, who was one of the country's leading thermodynamicists, and all of the tricks for splitting partial derivatives came into play. And all of the Maxwell identities, you may have heard about Maxwell identities in thermo. Well, we had to use all of them a lot. And it took the three of us several months. And at the end of the several months, we were each convinced that the other two guys had done all of the work. It was a very difficult calculation. But we got it to work. And you can read the paper for yourself in molecular physics and see how it works, and you can read through all of the thermodynamic parts and learn how to use thermodynamic identities. Or some of my past students said, learn how to realize why there are other things in life than thermodynamic identities. Okay, now we come to the other important issue about Mori-Zwanzig. It is almost never the case that you find anyone evaluating phi of s by looking at the structure of the projected dynamics. Almost always people make ad hoc approximations about phi of s, namely number times delta function, or maybe number times decaying exponential. What Rachel Nasto targeted in her master's thesis and basically pulled off, admittedly for a very simple case, was the direct evaluation of a projected memory kernel. What do I mean by that? Well, let us go back to 2657. 2657 says that the memory kernel is f of 0 times f of s. But if you go back to f of s, you notice that f of s is determined by its value at time 0 times what looks at first like a Liouville operator. This is equation 2645, except if you look at equation 26.45, the argument of that exponential has got a Liouville operator in it, it's got a time, and it has that I minus p. That is, the evolution is done by means of the projected dynamics. Almost nothing is known about the nature of projected dynamics. People make assumptions which allow them to say the projected dynamics get me back to the equations I think I was aiming for. And in this case, it's very useful. The Mori-Zwanzig equation is a bookkeeping method which tells you how to generate all of those thermodynamic derivatives in the denominator and get the right derivatives in the denominator. It's a great bookkeeping technique, believe me. Of course, then you have to evaluate the thermodynamic derivatives. This is a little more challenging. However, Rachel, well after this book was written, was able to do an true evaluation of projected dynamics. I can give one more case of evaluating of projected dynamics. One of my undergrads, John Stott, did a computer simulation of an Ising ring, Ising lattice. It's magnetic spins and they speak to their neighbors. And there was a form for the relaxation, and what I said is we can numerically extract from the computer simulation and saying we have one variable and we can see its time evolution, and therefore we can extract the Mori kernel itself from a computer simulation. That's not exactly the same as extracting the projected dynamics. We have extracted f of 0, f of s, so we see the correlation function of the projected dynamics with f of 0. He did that. Most people do not worry about this. And I will now give a case where this blows up. Suppose our one variable is a of q. It's the spatial Fourier component of the density of diffusing particles. If you turn the crank on the stick this variable in and say we're going to do diffusion and we're going to get out how this one variable relaxes, you eventually get a memory kernel phi. And what has typically been done is to say, I see phi, I know these are diffusing particles, and therefore phi is q dot diffusion tensor dot q. Yes? And people do this and it looks natural, but they never evaluated the Mori kernel. Well, you can also do the calculation without invoking the Mori kernel. And if you do that, you discover that if you have interacting particles, the correct identification for phi was q dot d dot q plus iq grad, and then there's a beta, and there's a dij, and the divergence of the diffusion tensor is not 0. And if you did not realize what you were doing, you would have generated, without thinking, the wrong kernel. And therefore, calculations in which I say, I have done all the Mori-Zwanzig work, and then you just lazily write down the kernel, are in grave danger of being potentially wrong. Okay, and I talk about things a bit more. And having said I talk about things a bit more, there are some other places where you can go wrong. For example, you could try using the Mori-Zwanzig equation to do a calculation of a system that is not in thermal equilibrium. And if you do that, you get wrong answers again. Well, we are out of time. We have discussed the Mori-Zwanzig equation. We have gotten to the end. I think you have enough homework left to justify being in the course. We did, however, get to time evolution, as I promised, though maybe not quite as much as we could have. However, this is the final lecture. We are done with the course.